Hey there everyone, today we're doing Chapter 2, Section 2, Day 1. It's on polynomial functions, which is something that you should have been introduced to in Algebra 2. But I wanted to show you a quick example and a non-example of a polynomial function. There's a couple of requirements. A polynomial function should be defined everywhere, so it's continuous. You can input any values. There's no restrictions on the domain. And it should have smooth, rounded turns in it. So those are the expectations you should have when you're graphing any polynomial. What polynomials aren't is they don't have any jumps or discontinuities in them, and they don't have any breaks or edges like you see in this graph over here. Okay. Now you may be wondering, what exactly is a polynomial function? Well, a polynomial function is any function that has terms of varying degree being added or subtracted. So for example, x to the third plus 2x squared plus x minus 1. That's an example of a polynomial. All of the terms are varying degrees, and there's no rational fractions in there. There's no square roots. This is considered a polynomial function. Okay. Remember, polynomial literally means many numbered or many termed function. Okay. So here's some examples of some peculiar types of polynomials. First of all, the constant function is technically a type of polynomial. There happens to be no degree in it, which means there's no variable. So you get this constant flat line. But it's still technically a polynomial function because we can write it like this: f of x equals 2x to the 0 power. Okay, that would mean the constant 2. X to the 0 power is always 1, and so this is always a constant 2 value. This graph is the constant value 3 up here. Linear functions you should be familiar with. Those are when you have degree of 1. So that's anytime you have an equation of a line. That's technically also a polynomial. So like f of x equals 2x plus 3. That's a polynomial function. And then you've hopefully are very familiar with quadratic functions. These are the ones where you have degree of 2. F of x equals x squared plus 4. So these are just three of the most basic types of polynomial functions. For the most part in this section, we're going to focus on the polynomial functions with degree 3 or more, because those are the more complex ones. When you are trying to decide the end behavior, we've talked about end behavior in Chapter 1. When you're trying to decide the end behavior of a polynomial, there's a definite pattern to it, and it has to do with the degree that is on the leading term as well as the positivity of the leading term. So if the leading term is positive, then your, I always look at the right end behavior, then your right end behavior will be going up. So in these two cases, you can see that the leading term is positive, so it's going up towards the right. The other side is determined on whether or not the degree is even or odd. If the degree is even, then the end behavior is the same on both sides, so it'll be up and up. If the degree is odd, then there'll be opposites on both sides, so it'll be down and then up from left to right. If your leading term is negative, then the right side of your graph will be going downward, but the other side will always still follow the first rule. If it's an odd exponent, then they'll be going in opposite directions. If it's an even exponent, they'll be going in the same directions. So I kind of use this little chart, and this is probably what you should copy down. If you have even degree, then it'll either be up and up or down and down. If you have odd degree, then it'll either be down and up or up and then down. Okay. And what will determine which of those depends on the positivity of your leading term. So it'll be one of the top two cases if the leading term, and I abbreviate that LT, is positive, and it'll be the bottom two choices if its leading term is negative. So using this table, you can really quickly determine what the end behavior is going to be of your polynomial function. Okay, so let's go ahead and do that in some practice over here. If you didn't get a chance to copy down that table, you might want to just pause the video and go back and copy that into your notes, because I'm going to be using that table for these problems. Okay. For example 2, they want us to describe the end behavior of the graph of the polynomial function using limits. That's what we've been practicing doing from chapter 1. Explain your reasoning using the leading term test. So all your reasoning has to be is identifying the leading term. So the leading term for letter A, leading term is the largest degree term. That would be the 3x to the 4th. Now, if it's in standard position, it should be the first term, but it may not always, if you look ahead at B, it may not always be in the front position. So you just have to double check. This one is the highest degree and it's in front, so that's the right one. And so the first thing we notice is that 3x to the 4th is positive and it's even. The exponent is even. That's what you're checking to see if it's even or odd. So because it's positive and even, we know that the end behavior should be up and up based off the table. So we're going to go ahead and write the end behavior now as the limit as x approaches negative infinity, f of x will equal infinity, and the limit as x approaches positive infinity, f of x will also equal infinity. Okay, and that's all you have to do for your end behavior. This will be the reasoning of the leading term test, that you found the leading term and identified it as positive and even. So if we look for our leading term in B, our leading term would be negative 2x to the 7th. So we're going to write that leading term down. The exponent of this leading term is odd, but the leading term itself is negative. So this is a negative odd leading term. So our end behavior will be the limit as x approaches negative infinity. So I think of it this way, okay, it's odd, so they have to be going in opposite directions, and it's negative, so the right side has to be going down, because it's negative. So the right side goes down, the other side has to go opposite. So it's going to be up on the left side, or up on the negative side, and then down on the right sides. So as x approaches negative infinity, f of x is increasing, so it's going towards positive infinity. As x approaches the right side of the graph, positive infinity, the function, the y values are going down. Okay, and for our last one, we have a very simple one. Our leading term is x cubed. This is still positive, but it's odd. And because it's positive, I know that the right side of my graph, as I get larger and larger, should be increasing. And because it's odd, I know that they should be going in opposite directions, so the first part of my graph should be going down. So that means the limit as x moves to the left, the function is decreasing on the left side, so it's going towards negative infinity. And the limit as x approaches positive infinity, the function will be going up, so it will be going towards positive infinity. Okay, so that's the leading term test. Try these two really quickly. Okay, make sure you identify the leading term correctly and that you have the right notation for your limited end behavior. Okay, the next thing we're going to do is we're going to be solving for some other characteristics of the polynomial functions. One vocabulary that I want you to write down is turning points. A turning point is located on a polynomial when it changes from increasing to decreasing or vice versa. So it's the point where the function changes from increasing to decreasing, or vice versa. You may notice, if you think about it, this is the same locations as our extrema. Those are the turning points of the graph. Okay. Now there is a little bit of a concept for turning points. If you have a function, a polynomial function, and you can identify the degree of that function, meaning the highest degree, that'll help you determine how many turning points it can have, as long as that degree is greater than 1. So if you know the degree, that tells you two things. It tells you first the number of zeros. We talked about zeros. Zeros are the same thing as x-intercepts. It'll have at most that many. So it may not have exactly that many, but at most it will have that many zeros. And at most it will have n minus 1 turning points. Okay? So you can never have more than these values of turning points and zeros once you figure out the degree of the function. Let me show you how that works in example 3. The first thing you're going to do is state the number of possible real zeros. Remember, that means x-intercepts. And turning points, that's like your extrema for this function. So the first thing we want to do is we want to identify the n. The n is the largest degree, which would be 3 in this problem. So n is equal to 3. And so that tells me that there could be at most, make sure you write at most, 3 real zeros and at most 2 turning points. Okay, that's what we can determine just by looking at the highest degree. All right, the second thing they want us to do is determine all of the real zeros by factoring. So in polynomials, just like we were finding zeros in our functions in chapter 1, we're going to be searching for our zeros, but we're going to be taking this polynomial and setting it equal to 0. So we'll get that 0 equals x cubed minus 5x squared plus 6x. Your first step is to always look for the GCF and factor out the greatest common factor from all of the terms. This one happens to be an x, we can factor x out. So this becomes x squared minus 5x plus 6. And then we're going to factor this quadratic trinomial to be x minus 3 times x minus 2. So then we can set each factor equal to 0, and we would get that x is 0 at 0. So it has the coordinate 0, 0. X is 0, or sorry, the function is 0 when x is 3. So that would be 3 comma 0. And the function is 0 when x is 2. So 2 comma 0. Those are your 3 zeros for the function. Could there be any more? Well, we know that there are at most 3 real zeros. So we found all of them. Okay. Try this one on your own. Okay, so if you answered this one correctly, you should have found the zeros to be at 0, 0, 9, 0, negative 3, 0. And there should have been at most 3 real zeros and at most 2 turning points in the function. Okay. All right, the other type of polynomial that we're going to see are polynomials that are in quadratic form, but maybe not necessarily quadratic form with degree of 2. This quadratic form actually can be solved like a regular trinomial, but we're going to have to do a little bit of manipulation. So I wanted to remind you how to do these types of problems. We're still going to state the possible number of real zeros and the turning points. So our degree for this one is 4, and is 4. So we could have at most 4 real zeros and at most 3 turning points. Okay, we're going to set it equal to 0 just like we did in the previous example. But you may be unfamiliar with how to factor this with a fourth degree term there. We can actually rewrite this. X to the 4th power is the same thing as x squared squared. And if we think about this, this is the same thing as x squared to the 1st power. And so now we have what looks like an actual regular trinomial, x squared squared minus 3x squared minus 4. So we just kind of have to imagine it's a regular trinomial with, and sometimes I have students replace x squared with another variable if that helps. So if you want to, you can visualize x squared as being like a, for instance. So this becomes a squared minus, remember x squared is really a, minus 3a minus 4. And this is something that's very easy for you to visually factor. We just have to remember that a squared represents x squared. So now I can factor this and say that it's going to be a minus 4 times a plus 1. And then if we're trying to solve for x, we need to replace the a's back with the x squared that we had them originally set equal to. So then this will turn back to x squared minus 4 times x squared plus 1. And we can factor once more. This is a difference of squares. X squared minus 4 factors to be x plus 2 times x minus 2. And you cannot actually factor this one. So this is x squared plus 1. You have to leave it like that. When we solve this, you will be able to solve for these two factors. The zeros will be at negative 2, 0 and 2, 0. But we won't be able to find any zeros for this part. So remember, that's at most 4 real zeros. You may not have that many.